Hey everyone, and welcome. I'm Adrienne Stenz, Application Engineer for YSI IQ SensorNet, and today I'm joined by John Downey, Veolia Instrumentation Technician at Brockton Advanced Water Reclamation Facility. In this webinar, we are going to be spotlighting Brockton AWRF and diving into their sensor-based aeration control system. Here is an overview of what we will cover today. I'll start by providing an overview of Brockton AWRF and talk a bit about its process, effluent limits, and a bit about the plant history. Next, John will cover where all of the online sensors are located within Brockton's process and how they're used. Then John will share his preventative maintenance schedule for the sensors and his tips for ensuring accurate and reliable data from them. I will finish the presentation off with a comparison of the two different aeration control methods used at the plant, ammonia-based aeration control and dissolved oxygen control, including a comparison of the blower energy performance for the month of June 2024. Finally, we'll open things up for discussion and Q&A. In the meantime, if you have any questions, please feel free to drop them in the chat. So let's get into the presentation. Brockton Advanced Water Reclamation Facility is a large wastewater plant located about 30 miles south of Boston, Massachusetts, averaging about 14 to 18 million gallons per day. The influent water for the plant is mainly residential, serving 3 communities that total about 130,000 residents. They also have 2 septage receiving sites, an industrial pretreatment program, 2 public hospitals, and 1 VA hospital that discharge into the wastewater plant. There are 4 primary clarifiers at the plant located here, followed by 7 aeration basins, 4 on the north side of the plant and 3 on the south. The north aeration basins total 5 million gallons of basin volume, and the south total 4.5. Each north and south side have dedicated secondary clarifiers for their aeration trains. This is an aerial photo of the north aeration basins. At the time of this photo being taken, Basin 1 and Basin 2, which you can see here, were drained. These are each 1.5 million gallon tanks. Basins 3 and 4 are closest to the blower room in the back of this photo and are each 1 million gallon tanks. The primary clarifiers are located over here on the right. Both the north and south aeration trains at Brockton are 4-stage Barden-Foe processes, making use of a pre-anoxic, aerobic, post-anoxic, and post-aerobic zone to optimize total nitrogen removal. These north trains are run on ammonia-based aeration control via an ammonia sensor, which sits right here in the aerobic zone. North Aeration Basin 1 was drained for the month of June, so here is a cool photo of what that basin looks like while it's drained. This is the post-anoxic zone of the basin, which is outfitted with diffusers and a mixer to operate as a swing zone. There's also baffle walls in this zone to slow the movement of the water. These basins are about 20 feet deep. This is an aerial photo of the 3 south aeration basins of the plant, which is a little hard to see, but you can see the air mains for Basin 5, Basin 6, and Basin 7 here. The south aeration basins are also 4-stage Barden-Foe processes, making use of the same anoxic and aerobic zones as the north. But the south trains are a little different as they are wraparound ditches that operate via dissolved oxygen control. This is what the south aeration basins look like. These are ditches with an aerobic zone that spans the back half of the ditch. This photo is actually half Basin 6, half Basin 7, but it gives you a clear picture of how the ditch wraps around and the difference between the anoxic and aerobic zones. Here's another photo showing the aerobic zone for South Basin 7, 6, and 5. So a bit about Brockton AWRF's plant history. In 2016, part 4 of a 3-stage upgrade was started to implement ammonia-based aeration control at the plant. That year, a head-to-head trial with 3 manufacturers' ion-selective electrode ammonium sensors was held to determine which would work best for Brockton, since having a reliable ammonium sensor is very important for ammonia-based aeration control. Dave Norton, the contract administrator at the time, led this great project, knowing all of this. In 2018, YSI was decided as the instrumentation manufacturer for the project due to our ammonia ISE sensors accuracy and the benefits of our 2020 IQ SensorNet controller system. In 2020 through 2021, all of the aeration basins were outfitted with new aeration equipment and online sensors, starting with the north basins and continuing with the south. In 2021, trials were done in South Basin 5 to determine the ideal sensor placement for the ammonia sensors used in the ammonia-based aeration control system, with trials being done for a period of 7 months. We have a great application note written on this trial that you should check out that talks about the ideal ammonia ISE sensor placement for ammonia-based aeration control. This is the NPDES permit for Brockton in relation to ammonia nitrate effluent limits. The main goal of the plant when undergoing the aforementioned upgrade was to improve their aeration efficiency while also meeting their stringent effluent limit of 3 milligrams per liter total nitrogen. Brockton AWRF discharges into the Salisbury Plain River. And this river is actually considered impaired or polluted up until the point where Brockton AWRF discharges. Past the wastewater discharge point, the river is actually clean enough to be considered unimpaired or not polluted. So this is super cool because Brockton AWRF is actually discharging water into the environment that is making it cleaner than it currently is. And with that, I am going to turn it over to John Downey to take it for a bit from here.
Thank you, Adrienne and Shannon. Good afternoon, everyone. I'm John Downey, a Veolia's instrumentation technician here at the Brockton Water Reclamation Facility. It's been the advanced water reclamation facility for a very long time now, and that's owing to the city's interest. And as Adrienne mentioned, particularly that of the city's recently retired contract administrator, Dave Norton. Trying new methods like ammonia-based blower air control for biological nutrient removal requires a champion. I think any of the superintendents on this call could attest to that. Dave was that champion for Brockton in this facility, and I think Dave and the city have a very good partner for the project in Veolia, who oversaw the integration of this method into the plant's overall process control. Ammonia-based blow control is a concept I've been talking about around New England for about 13 years now, participating in various trials and upgrades. So when Veolia asked me to join the Brockton team for this implementation, I was very excited. Brockton's aeration capability, as Adrienne just laid out, incorporates 7 basins, 4 in the north and 3 on the south side of the plant, fed from 4 primary clarifiers. The north side is fed through 2 flumes, while we feed the south through a primary effluent pump station. And we've got a pump all the way across the plant for that. Thank you. And you can see in this slide, these are the north basins. Shot was taken from the roof of our administration building. Thank you very much, Shannon. The basins in the foreground, as Adrienne said, are 1 and 2, respectively. And you can see we have basin 1 taken offline here. Remember that. It'll be important later in the slide that Adrienne is going to talk about. Two basins in the background are the basins 3 and 4, and behind them is our north lower building. Flow moves right to left, and you recognize that Godwin pump up in the far right side there, uh, just just next to the partial flume that feeds both basin 1 and 2. The covered primaries are on the far right. It's fortunate we have basin 1 offline. You remember the baffle walls from Adrienne's introduction. They're arrayed throughout these basins. They were installed as part of this upgrade to slow down the velocity and provide some separation of aerated and anoxic zones. Basin 1 and 2, as Adrienne mentioned, are 1.5 million gallons. 3 and 4 hold 1 million each. While these 4 basins are fed from a common source, they are 4 separate environments. This is owing to the way they're fed. You can see those covered flumes are at an angle to the basin head. So, and the flow is further directed by a rudder at the end of the chute. Perhaps it's more of a suggestion than a direction we give it, because the water seems to go where it wants sometimes, but we get pretty good filling overall. What complicates this is how we feed the RAS. RAS is being fed into the right side of each of those chutes, just below the flumes. And the RAS tends to hug the right wall of the chute going into the 2 basins. Solids from the primary tend to hug the left wall. That doesn't mean that we're sending all the RAS to one and all the primary solids to the other. We do get both flows into both basins, but we do get a bit of a different environment in each because of this. The same is true for basins 3 and 4 as for 1 and 2. So with that as our workspace, let's look at how we monitor what's happening here. It's a little easier to talk about the placement of the sensors themselves with a diagram. So we're changing orientation for this part of the discussion. In this slide, the basins are 4 through 1, bottom to top. Each basin is divided into 4 zones, beginning with an anoxic influent, an aerated zone, another anoxic zone, and an aerated zone at the effluent. You can see the placement of our internal recirculation pump, those black stop signs there, which are at the end of the aerated section. This brings fully nitrified, or as fully nitrified as we're going to get, liquid back to the basin head, where it re-enters the basin directly below the inlet. Ammonia is the controlling parameter for this network, but it's not the only measurement we need. We'll start with some points of dissolved oxygen. In this case, at the beginning of the aerated zone, about 2/3 of the way through the aerated zone and at the effluent. We add to these 2 points of nitrate measurement in the influent just before aeration begins, and about halfway through the downstream anoxic zone. At these 2 locations, these sensors are measuring how well we're converting nitrate to nitrogen. The upstream sensors should theoretically show us the lowest NO3 value in that particular basin. pH is measured at the effluent. And here are the north side control points now. Originally, these were located downstream of the midpoint dissolved oxygen sensors. They were in the vicinity of the recirculation pumps, which is the spot in theory after which we're not going to convert any more ammonia to nitrate. This is a very reasonable choice at the time it was made, given the process conditions. As we've mentioned, there are 7 aeration basins here. So normally the total influent is split among all of them. During construction, 1 or more basins were always offline, meaning that the same flow, the same loading was being distributed among fewer basins. That is, the same amount of ammonia is going into fewer basins. Now, why does that matter? Well, it has to do with how ion selective sensors, the ammonia sensor is an ISE, how that works, and the space required to convert NH4 to NO3. An ion selective electrode is sensitive only to ammonium ions. In order to maintain that sensitivity and service, the electrode needs to be in an environment where the concentration of NH4 is going to be greater than 1 part per million for a significant part of the day. Significance is a relative term here. But I would say for us anyway, 8 to 10 hours in any 24 is going to be sufficient. When we were under construction, with fewer basins receiving the flow, this requirement was pretty easy to fulfill. As more basins came online, the ammonia concentration was divided among more basins. More ammonia was being converted upstream. Uh, by the time flow got to the ISE, the concentration wasn't great enough to maintain that sensitivity needed. Uh, the answer for this is pretty simple: move the sensors upstream a bit. That would be the 7-month trial that Adrienne talked about. Uh, so you see here that our ammonia sensors on the north are about 30% of the way into the basin. And this is relatively uniform across the north side. Uh, Control points are indicated with the red dot, and you'll notice that there's also a red dot in the midpoint dissolved oxygen sensor. That's because we can run the north flowers from the ammonia signal or from the dissolved oxygen signal if we're performing maintenance on the ammonia sensors. These are some good shots of our sensor placements, and these are all in Basin 4. On the left, you see an ammonium sensor, and it's located at the spot where currently we are seeing less than 1 to over 4 part per million in a single day. And that's been fairly consistent. I'd say this just in this past 5 days, it's that high end is raising up to over 5. But it's just been fairly steady. In the center photo, we're standing at the head of Basin 4, and we're looking downstream. That black chain is holding the NO3 sensor, just where aeration begins. So again, at the end of an anoxic area where we're presumably converting nitrate to nitrogen. The effluent dissolved oxygen sensor is just downstream of that, and the ammonium sensor that we just talked about is on the other side of that walkway. The photo on the right is of the downstream NO3 dissolved oxygen and pH sensors. You can see the NO3 sensors close to the end of the anoxic zone from the angle we're looking at it. So this is more of what the north looks like. This is Basin 4 on your left side. That's our ammonia sensor. And that's about where we ended up with it. Moved it probably 3 times doing grab samples over the course of a month for that particular basin to determine where the sweet spot was, if you will. But it's been there now for almost 3 years, I guess. So it's worked well for us, and you can see how far up into the basin it actually is. There's an awful lot going on after it. Now we're over here on the south side. We're pumping primary effluent from adjacent to the head of the north basins across the plant. These 3 basins are fed by a common header. As with the north, despite a common origin, these 3 basins represent 3 different environments, owing to how they are filled and how they exhaust. Each basin fills by gravity off the header. Flow reaches Basin 5 first. Because of that, it tends to have the highest loading of the 3 basins. I suspect that played into its selection as the site for the pilot project. The city and the engineer, CDN Smith, had an idea of what to expect. Basin 6 features a split effluent weir, which restricts flow and creates a slower moving environment. And as an example of that, just this morning, our ammonia in Basin 5 and 7 were 0.7 and 0.8, respectively. The ammonia in Basin 6 was 1.3. It's all the same water, but that'll give you an idea of the differences you can have basin to basin. Basin 7, being at the end of the header, is the one basin where flow is actually being directed. There's nowhere else for it to go. We use another overview diagram to understand the south sensor placement. Flow in each of these basins makes a turn at the center of the walkway. And the sequence of anoxic and aerated zones is the same as in the north, but more pronounced. The internal recirculation pumps are located at the end of the aerated zone, pumping back to the head of the basin. The dissolved oxygen sensors are pretty much where they are in the north, with respect to the aerated portions of the basin. We again measure pH, the effluent. The nitrate sensors are located again to give an indication of how denitrification is going, both with respect to the recirculated liquid and to the effluent. As in the north, our ammonium sensors were originally located at the end of that horseshoe aerated zone. So right where you see the internal recirculation pumps. As the plant capacity came online, this placement was no longer workable. After some grab sampling, we determined the more serviceable spots for each sensor. You can see where they are now. Our control points are still the red dot dissolved oxygen sensors because we do dissolved oxygen control on the south. But the ammonium sensors provide good real-time performance data. And you can see the ammonium sensors not all in the same place. And that may not stand out to you here in the graphic, but some photographs would certainly point that out, that in Basin 6 and 7, they're much closer together, and Basin 5 is all the way down at the end of this walkway. Although the aeration grids are exactly the same. So there's a lot to think about when you implement these things. So what we've done is we've picked the spot in each basin that satisfies that requirement we talked about of having 1 part per million for enough of the day to keep the sensor fully sensitive to ammonia. And we're going to talk about that a little later in this presentation. Here are some of the south sensors. On the left is Basin 7 ammonium sensor. We recently had to move this to accommodate the efficiency of the conversion in the aerated zone that had been downstream. And we found we were converting ammonia faster, so we weren't maintaining 1 part per million for enough of the day for that to be a viable spot. So we brought it back upstream here. The center photo features the Basin 6 upstream NO3 sensor located at the end of a very long anoxic section. It gives you a better idea of how we're treating the recirculated liquid. On the right, Adrienne's standing at the controllers for these three basins. The controllers are where I start each day, and we'll talk about that in a minute. In addition to the aeration basin monitoring, the plants have 3 nitrate sensors downstream, one each at the effluent to the north and south secondaries, one at the effluent channel just ahead of the UV disinfection. This one here we're looking at is on the north side. We're going to talk for a minute about maintaining these 52 sensors. And first off, I'd like to point out that each one of these has air compressor cleaning, the cycle of which is controlled either by a schedule that we set, or in the case of the nitrate sensors, by the sensor itself. The dissolved oxygen sensors are automatically cleaned every 2 hours, the pH about every 30 minutes. The ammonium sensors are cleaned every 20 minutes, and the nitrate sensors about every 90 seconds. This is a combination of a 10-second air blast and some ultrasonic pulsing on the sapphire windows of the sensor. 4 years into this, I can say that the schedule works pretty well, but it doesn't eliminate the need for some regular checking. And here's how we approach the maintenance of these sensors. Given that there are 52 deployed across the plant, each day I like to get a quick idea of where we are. The network hardware makes this pretty simple. Starting at the effluent of the plant, I walk to each sensor controller location, which has a display incorporated in it, to check the performance of the sensors since the previous morning. Basically, I'm looking at a graph for the last 24 hours, first to confirm that it is not a flat line, and even pH is not completely static, and that the range that's measured is plausible. Anything out of the ordinary lets me know that I may need to investigate further. Since the controllers for the north aeration are collected in one place, the controllers for the south are together in another, as we saw on the slide with Adrienne a few minutes ago. Checking the performance of the sensors is not overly time-consuming. We have 2 formal preventative maintenance work orders for aeration. The first is for a check of the dissolved oxygen sensors, which is required weekly. On the north side, each dissolved oxygen sensor is placed in hold so that the signal back to SCADA remains static during cleaning. Each sensor gets pulled out of the basin, wiped off with a damp towel, and returned to the basin. It's important wipe the sensor, not because they collect a lot of heavy solids, because they don't, uh, but to remove any invisible films that may interfere with the sensor function. I haven't run into that here that I'm aware of, but I have seen it over the past 20 years in different sites. Um, when I move over to the south, because we're using dissolved oxygen as the control point, rather than just place that sensor in hold, I changed the control strategy over to airflow mode. Um, and I let the chief operator know that we're doing that. So he'll know that we've changed the process logic a little bit during the cleaning cycle. Once the sensors are back in the basin, they return to the actual concentration of DO in the water fairly quickly. And after that, I can switch control back over to DO mode. Um, Having cleaned the sensors, I use our lab's handheld to dissolved oxygen sensor to compare with the network sensors. This is pretty straightforward in that these sensors are the same technology. They're both fluorescent squelching, or what's commonly referred to as optical. The things to consider when comparing any two sensors, how they actually operate. As I said, the network and the handheld use the same methodology. That doesn't mean they're the same. The network sensor will hold the calibration for its entire service life. It also has a T90, that is a time to reach 90% of the actual parameter concentration, about 3 minutes. The handheld device we are using must be calibrated once a week. However, it's much more reactive and it reaches a stable state for measurement in about 10 seconds. To accommodate the difference in function, I will immerse a handheld sensor next to the network sensor to be assessed, then walk back to the control room to get a display. The extra minute or two before starting the comparison measurement usually saves multiple readings, and acceptable results, for me anyway, are within a quarter part per million. I note the handheld and network readings and have kept a spreadsheet of this data since October of 2020. This slide from Basin 5, which went online in February 2021, is an example of the actual dissolved oxygen performance. If you're going to do process control, I think this is the kind of reliability I think you'd want. It helps, though it isn't strictly necessary, to take these readings when the blowers aren't ramping up quickly so that both the network and handheld sensors aren't chasing a rapidly changing concentration. We do something similar with our ammonia sensors, but on a monthly basis. One feature of the ion-selective electrode I really like is it seems impervious to pain. I've taken grab samples next to heavily fouled sensors and found that the readings are very close to the lab result. So rather than cleaning each sensor manually, I take a grab sample and compare the results, and then may manually clean based on what I find. The key to keeping an ion-selective electrode serviceable is to verify its function and adjust its slope periodically. Once per month is a good interval for this. A prerequisite for this exercise is that the actual concentration of ammonium in the basin be 2.5 part per million or less. The reason for this is the acuity of the measurement we're looking for, especially if we're going to make an adjustment. Commercially available grab sampling of ammonia, as you probably are aware, typically offered 0 to 2.5 part per million range and 0 to 50 part per million range. The 0 to 2.5 part per million range test allows us greater certainty about the concentration of the grab sample. The other requirement is to filter the grab immediately. This is because the concentration of ammonium can change rapidly and skew your results. The operation takes me about 40 minutes per sensor. It may need to be repeated in cases where the actual basin concentration is less than a part per million, but the sensor is reading greater than 1 part per million. When adjustment to the sensor slope is needed, that has to be done when the actual concentration is above a part per million, And to ensure accuracy, I prefer above 1 part per million, but equal to or below 2.5 part per million. Uh, as with the dissolved oxygen checks, I've been keeping a spreadsheet of the results since before this task became a formal work order. When I do remove these from process for cleaning, as I'm doing in this slide, I use a damp paper towel and I'm careful not to be aggressive with the membrane. Most important thing I do with any of these sensors is to look at the curves for the previous 24 hours. It's a great way for me to know what's happening, pick up on something that doesn't make sense, or to identify a specific point for attention. Uh, it's on that basis, say that I will select the nitrate or pH sensor for maintenance. Since these are not part of a formal work order system, uh, there's no set schedule. So it really will be an ad hoc situation based on what I'm seeing in the curve, or perhaps a grab sample I might decide to take. Uh, pH electrodes, I'll calibrate before installation, and then clean and calibrate quarterly. And that schedule is based on my experience with multiple vendors over 20 years. Uh, the reference junction fouling is really minimal, owing to the fact that we have these at the effluent of the basin. Uh, the nitrate sensor cleaning can be a lot more involved, requiring weak acid, isopropyl alcohol, edisonite, or all three. Um, it's very much an ad hoc operation, as I said. Maybe we can visit that another time. Uh, we're determined that in the environment that we provide, an annual change of sensor faces keeps the networks running reliably. This means a 12-month service life for dissolved oxygen caps, for pH electrodes, and for the ISEs. Any of you who have this particular brand installed may have a different experience, but that's what we've found in 4 years of operation. It's been a pretty great experience, too. This isn't the best job in Brockton. I think I've got the best job at Veolia. Uh, I'd like to turn this back to Adrienne to look at the performance of the North and South Basins for the month of June.
Nice. Thanks, John. So Brockton is a unique plant that is currently running two different aeration control strategies. The North aeration basins are run on ammonia-based aeration control, with control coming from one ammonia ISE sensor located about halfway through the aerobic zone, which you can see a photo of here. Backup control for these basins comes from a DO sensor located further downstream, about 3/4 of the way down the aerobic zone. The ammonia sensor readings control blowers via a variable ammonia scent point of 1 to 5 milligrams per liter. And these are some photos of the controller screens showing the ammonia concentrations over a 24-hour period on the left and over a weekly period on the right. The ammonia sensor ranges from 0.5 to 5 to 6 milligrams per liter daily trending upwards throughout the week towards peaks of 8. These are the blowers for the North aeration basins, controlled via a variable set point of 1 to 5 milligram per liter ammonia. Airflow to these basins is controlled via a butterfly valve, like the one shown in this photo here. One 300 horsepower turbo blower and one 200 horsepower turbo blower are manifolded together to supply air to North Basins 1 and 2. And one 300 horsepower and 150 horsepower blower are manifolded together for North Basins 3 and 4. This makes the total available horsepower for the North Basins 950. Typically, only 2 blowers are running at once, one for North Basins 1 and 2, and one for North Basins 3 and 4. The South Basins, on the other hand, are run on dissolved oxygen control, with control coming from the DO sensor located in the last third of the aerobic zone, which you can see a photo of here. The blowers are run at a direct set point of 2.5 milligrams per liter DO, which you can see a photo of the blower control panel screen here with the set point indicated. This set point can be manually adjusted as needed. These are the blowers for the South aeration basins. There are 3 older centrifugal blowers that are 300 horsepower and 2 newer 150 horsepower turbo blowers that are all manifolded together to supply air to South basins 5, 6, and 7. The airflow is controlled via a butterfly valve, same as the north side. Not all blowers are on at once. Typically 2 blowers are on for the south, sometimes only 1. Brockton pulls all of its data into a really great SCADA system with a photo of that being shown here. And we thought it would be cool to pull a month's worth of SCADA data from the plant to evaluate the energy consumption and the treatment efficiency between the 2 different control methods used at the plant, ammonia-based aeration control and dissolved oxygen control. We ended up pulling data from June 2024, which was a month with enough sensor, blower, and flow meter data for us to evaluate. Some considerations for the month of June were that North Aeration Basin 1 was taken out of service to perform maintenance on the basin. Since North Basin 1 and North Basin 2 share a common flume from the primaries, this means that North Basin 2 saw an additional volume of flow for the time period. Additionally, primary clarifier 3 was out of service for the month of June, so the primary clarifier volume was down 25%. There were 2 SCADA dropouts during the month of June from June 2nd through June 4th and June 7th through June 10th, giving us 23 days of data for the month to evaluate. This was the flow split in MGD between the North and South basins for the month, with North basins being the green line and South basins being the blue. As John explained earlier, the North and South basins do not treat equal volumes of flow. The North basins are located directly off the primaries, while the South basins are a bit further away and require pumping. Additionally, the North basins have a slightly larger tank volume. You can see here that for every single day throughout the entire month of June, the North basins handled more flow than the South. And on average, the North basin saw 17% more flow than the South for this month. These are the DO levels in the North aeration basins throughout the month, coming from a DO sensor located in the aerobic zone. This gap in data here is when the SCADA system dropped out. North Basin 2 is indicated by this orange line, which obviously jumps out at us since the DO levels seem excessively high in the basin, with an average around 3.5 milligrams per liter and peaks up to 6. The reason that the DO levels were so high in North Basin 2 was because Basin 1 was offline for this month. The aeration control system for North Basin 1 and North Basin 2 are tied together. North Basin 1 was drained for the month of June for maintenance, but still needs to maintain a minimum mixing airflow in the basin to keep equipment healthy and to prevent things from going septic. In order to maintain that minimum airflow in North Basin 1, the North Basin 2 airflow must be adjusted and bumped up a bit. Since the DO levels were inflated for North Basin 2 to account for North Basin 1 being offline, let's take a look at the performance of North Basin 3 and 4 in terms of DO. North Basin 3 is the light green line and North Basin 4 is the dark green line. North Basin 3 and 4 DO levels oscillated between 1 to 3.5 milligrams per liter for the month of June. Both had very similar DO performance with an average DO around 3 milligrams per liter. These peaks that we're looking at for DO are broader and more capped, indicating that DO levels are rising and stabilizing at a relatively higher level for some time before gradually decreasing, suggesting a steady and sustained aeration response, typical of what you see in ammonia-based aeration control systems. These were the ammonia concentrations in the North Basins for the month of June. North Basin 3 saw the bulk majority of the ammonia load in the North Basins during this time period, with average peaks near 5 milligrams per liter ammonia, with one day reaching a peak of 9. Though North Basin 3 saw the bulk load of ammonia, you can see the system does a pretty effective job at bringing those ammonia levels down to an average of around 3 milligrams per liter. The ammonia loading across the basins became more evenly distributed towards the end of the month past June 26th. North Aeration Basin 2, indicated by the orange line, saw the lowest ammonia concentration across the basins, which makes sense since it saw a larger volume of flow, on average treating the same volume of flow in MGD as North Basins 3 and 4 combined. Thus, it had a diluted nutrient concentration. You can see the ammonia sensor for North Basin 2 does a really good job at catching both the minimums near 0.3 milligrams per liter, as well as the peaks of up to 3 milligrams per liter that pass through. It's cool to see these peaks, which show not only the diurnal loading of ammonia in the days with daily peaks and daily troughs corresponding to the daily variations in flows and loadings that the plant sees, but this also tells us a little bit of how the control system is responding. After our peaks of ammonia come through, the decrease suggests the control system is starting to increase aeration. This small bump here indicates a brief rebound of ammonia, which might be due to the delayed control response or just be from the natural dynamics of the process, since these microorganisms take time to respond to changes in conditions. Keep these rebound peaks of ammonia in mind as we look at the performance of the South Aeration basins in a few slides. These were the average DO and ammonia levels in the North Aeration basins for the month of June. Starting with DO, the average was around 2.7 for Basin 4 and 2.8 for Basin 3. This is a little surprising given the ammonia levels in the basins were so different, with North Basin 4 having an average near 1.5 milligrams per liter ammonia, and North Basin 3 seeing almost 2 times as much at 3 milligrams per liter ammonia. However, it does make sense given the control setup of a variable ammonia set point of 1 to 5 milligrams per liter ammonia. North Basin 3 only saw peaks of ammonia above 5 milligrams per liter on 5 separate days during the evaluated period. So it would make sense for DO to ramp up in the basins only on those days. Considering this, it makes more sense that the average DO levels for North Basins 3 and 4 were around the same. North Basin 2, we already talked about why the DO level was so inflated near 3.5 milligrams per liter to compensate for North Basin 1 being drained. The average ammonia concentration in North Basin 2 was 1 milligram per liter as a result of diluted flow kept at 3.5 milligrams per liter DO for a month. These are the DO levels in the South basins for the month of June. You can see much more consistent DO performance across the South basins when compared to the North, obviously, since these are run on DO control, maintained at a set point of 2.5 milligrams per liter, which you can see as the average here. There was one spike on June 11th for the South Basin 5, but other than that, the basins had pretty consistent performance. These peaks on DO are much sharper and narrower than the North basins, indicating a quicker change in respect to the DO concentration. The aeration grid in the South basins is all on-off, so the cases where we see minimum DO levels near 1 milligram per liter are likely when the aeration grid is all off, and then once DO levels fall below 1 milligram per liter, it looks like the system picks back up to try to maintain a 2.5 milligram per liter set point. These were the ammonia concentrations in the South basins for the month of June. Since primary flow to the basins is supplied through a common channel, with South Basin 5 being the first to receive water, South Basin 5 sees the majority of the nutrient load. South Basin 5 saw average peaks near 3 to 4 milligrams per liter ammonia throughout the month of June. You can see at the end of the month, the nutrient load evens out across the basins, with South Basin 7 trending upwards in ammonia concentrations throughout the whole month. These trend lines, similar to the North Basins, show the diurnal loadings of ammonia that come into the plant. You notice, like in the north, the ammonia levels fall, then spike and rebound. This rebound in ammonia level is higher and steeper for the South Basins when compared to the North Basins, whose rebound ammonia peak seems to be smoothed out a bit by the ammonia-based aeration control system, though not completely optimized. The ammonia sensor in South Basin 6, indicated by this light blue line, is doing a great job of detecting both very low levels of ammonia near 0.2 milligrams per liter and still catching peaks up near 3 that pass through. These were the average DO and ammonia concentrations in the South Basins for the month. Obviously, DO levels averaged right about 2.5 milligrams per liter for all basins given the DO set point. The average ammonia levels in South Basin 6 and South Basin 7 were low, right below 1 milligram per liter for the month. Both these sensors are located pretty far upstream in the aerobic zone in the basins. For South Basin 7 in particular, it's located about 10% of the way down the aerobic zone, which begs the question, if these sensors are consistently reading ammonia levels near 1 milligram per liter, that far upstream into an aerobic zone, does the rest of the aerobic zone really need to be maintained at 2.5 milligrams per liter DO, or are we wasting energy? In terms of South Basin 5, which saw average peaks up near 4 milligrams per liter ammonia, the system does an effective job of bringing those levels back down. Let's talk a little bit about the effluent quality from the plant for the month of June. These are the averages for the month from the lab taken from effluent water samples. The facility maintained good quality effluent throughout the month with average effluent nitrate concentration of 1.02 milligrams per liter, an average effluent ammonia concentration of 0.08 milligrams per liter, and an average total nitrogen effluent concentration of 2.82 milligrams per liter. So both control methods used by the South and North Basins maintained the water within the effluent standards for the facility for the month. Knowing a bit about the nutrient levels in the aeration basins and the quality of effluent water that we got out of it, let's dive into the blower energy consumption. This is a graph of the total kilowatt hours consumed by the blowers for the South and North aeration basins for the month of June 2024. The South basins are the blue line and the North basins are the green line. This is the kilowatt hours summed for all 5 blowers on the south side and all 4 blowers for the north side. Just as a reminder, the north side has 950 horsepower available and the south basins have 1,200 horsepower available. But these blowers are not all on at the same time. Typically, only 1 or 2 blowers is running for the South Basins and 2 blowers are running for the North. Kilowatts, like horsepower, is a measure of power. And what we're looking at here is kilowatt hours, a unit of energy consumption, measuring the amount of energy used by the blowers over time. This data was pulled off the SCADA system, as each blower reports out its total kilowatt hours daily. Kilowatt hours is important because it's what energy bills are based on, typically charged at X amount per kilowatt hour. You can see here that the North aeration basins had a lower blower energy consumption than the South basins for every single day throughout the entire month of June. This is the total kilowatt hours consumed by the North and South basins for the month of June 2024. The North basins consumed around 110,000 kilowatt hours, while the South basins consumed almost 165,000 kilowatt hours. To calculate how much less energy the North basins consumed for the month, we can take this difference in totals between the 2 trains and divide it by the total consumed for the South to find that the North Basins consumed approximately 35% less kilowatt hours of blower energy than the South Basins for the month of June. This is a big difference, considering the basins are receiving, in theory, the same wastewater, but operating on different control schemes. Like I said, kilowatt hours is what energy bills are based upon, so we can assume this means that Brockton spent 35% less on blower energy costs for the North Basins than they did for the South for this month. Of course, the North and South Basins don't treat equal amounts of wastewater in MGD, so that should be considered to get a clearer picture of the difference in energy efficiency between these basins. This is a graph of the blower kilowatt hours, but normalized for wastewater flow in MGD. The difference in energy consumption between the two trains is even more dramatic when accounting the blower energy output for the volume of flow in MGD that the basins saw for the month, considering that the North Basins treated 17% more flow than the South. To account for the total volume of wastewater treated, I normalized the kilowatt hours of blower energy data by dividing it by the wastewater primary flow coming into the basins in MGD, whose values were taken from the flow meters that are tied into the SCADA system. This is that graph of blower kilowatt hours normalized for MGD. The hope in doing this is determining how much more efficient the North aeration process is at treating each gallon or each million gallons of water that it sees. This is the total kilowatt hours per MGD for the North and South Basins. The North Basins consumed approximately 11,000 kilowatt hours per MGD, meaning that the North Basins consumed 11,000 kilowatt hours of blower energy to treat 1 million gallons of wastewater, while the South Basins consumed approximately 20,000 kilowatt hours per MGD. We can take the difference between these two values divided by the South to find that the North Basins consumed 45% less kilowatt hours per treated MGD, or were 1.8 times more efficient than the South blowers per volume of flow treated. This is essentially saying that the South aeration blowers took almost twice as much energy to treat the same amount of wastewater, or at least they did for the month of June 2024, which is a huge difference. In looking at and evaluating all of this data, we can say that the North aeration basins treated the wastewater more efficiently, meaning with less blower energy, than the South aeration basins for the month of June 2024. Given that the North aeration basins are run on ammonia-based aeration control and the South are run on dissolved oxygen control, we can conclude that for at least the month of June, the ammonia-based system and dissolved oxygen system both treated the water to quality effluent standards, but the ammonia-based system did so at almost twice the efficiency of the dissolved oxygen system. Additionally, sensor maintenance and placement within the process are very important. Cleaning, properly checking, and validating your sensors can lead to these reliable, efficient wastewater treatment systems. You heard from John on his tips and schedule for verifying these sensors, and from the graphs we looked at of sensor data, you can see how his practices go a long way in maintaining these probes' ability to read accurately across their measuring range. And with that, I think we're kind of coming up on time, so we can open things up to discussion and Q&A.
Sounds good. Thanks, Adrienne. We did have some questions come in during the webinar. One of the first questions was, does Brockton have permit limits for TP?
Ooh, do you want to answer that, John?
Yes, we do.
And you guys remove phosphorus via baric,
We're
correct?
precipitating it out we have three ferric stations, one before the primary clarifiers, and then two at the end of the aeration basins. One is in the north, one is in the south. We've got very little phosphorus going out at this point. Where I haven't done a phosphorus test myself in a while. I haven't had to in quite some time, but I know the numbers had when I was doing it were extremely low.
Nice. And someone also asked,
Thanks,
what
John.
type of nitrate probe do you use?
I'm
And
sorry.
someone asked what type of nitrate probe Brockton uses. So they
Well,
use a UV nitrate probe.
right.
Do you want to talk a little bit about that?
Yeah, they're these are the UV 254 sensors. Um, the measurement is a spectral absorbance. So rather than ion selective sensor, as you can have an ion selective sensor for nitrate, this is actually reading NOx, nitrate and nitrite. Um, the advantage of that style sensor, particularly at the effluent of the plant, is you get extreme the acuity with the measurement when you're dealing with the measurements as low as we're talking about. It's important that that half a part per million, that 0.2 of a part per million, that begins to matter. So that's why we have the UV nitrate sensor as opposed to an ion selective.
Yes. I'm just looking at some of these other questions here. One of them is, what's the reason for a slightly different location for the ammonia sensor in South Basin number 6 and 7 compared to number 5?
In each basin, what we're looking for is the spot where we see at least a part per million of ammonium for, say, 8 to 10 hours during the day. The actual curve, the diurnal curve, would indicate that's more like 4 to 5, maybe. But we also know that we're going to have parts of the day we're not going to have very much ammonia there at all. It's important that the sensors see and be in contact with the concentration above 1 part per million to keep it sensitized. Not continually, but for some significant part of the day. And I say significant for us is 8 to 10 hours. And in each basin, that sweet spot is in a different place. That has to do with the fact that I've got 7 different biologies happening here. They're not all the same environment. The diffuser arrays, although they're all laid out exactly the same, they're fed a little bit differently depending on how far away they are from the blower. Diffuser heads get clogged at different rates as different solids loading in different basins. There are a lot of things going on that are going to affect how much ammonia is getting into the basin, how much ammonia we can treat. In basin 5, we have a condition all the way at the end of the pier that matches a condition nearly at the head of the aerated zone, the beginning of the aerated zone in basin 7. That's how the basins operate. So it's not so much to be uniform in terms of having them all be in the same location or distance, but for the sensor to be in that spot where it's going to tell us something of value, and also to keep the sensor functional. So that's why they are the way they are. And they're not all exactly in the same spot on the south either, but I mean on the north, excuse me, either. But they're a little more uniform on the north, and that has a lot to do, I think, with the way flow goes through those basins, not in a horseshoe like on the south.